Okay, so on Friday we started section 5.2 and we stopped with direct substitution, which was where you just plug it in, right? So today we're going to talk about synthetic substitution. It is a whole lot easier and quicker. It uses fewer operations than direct substitution. The only thing that's a little bit tricky is that if terms are missing, you need to remember that the coefficient is equal to 0. Okay, so for any missing terms, that means you have a coefficient of 0. So for instance, if I look at this first example, I've got 2x to the fourth minus 5x cubed minus 4x plus 8. So I've got an x to the fourth and x cubed, but I don't have what? What's missing? My x squared, right? So what you want to do is you want to think of it as what it really is 2x to the fourth minus 5x cubed plus 0 times x squared minus 4x plus 8. Okay, so do you understand now what I mean by putting in a 0 for the coefficient for the missing terms? Does that make sense? Okay, so what we do when we use synthetic substitution is we just take and use the coefficients. So whatever they give you for x, so in this case they told us x was 3, you put on the outside and then you list the coefficients in order by the degree, which I just saw that I wrote something wrong there. That was cubed. Okay, so you write them in order. So we've got a 2 x to the fourth, so 2 goes in my box, and then negative 5x cubed, negative 5 goes in my box, then 0, then negative 4, then 8. So you guys see where those numbers came from in the box? All right, so here's how it works. What I do is I take this first term and I just drop it down. And then I'm going to multiply the x value times what's on the outside of this little box. So 3 times 2 is 6. I put that in the box under the next term. Negative 5 plus 6 is equal to 1. Okay? So when I go this way, I'm multiplying. But then here I'm adding. Okay? Inside the box, we're adding. Okay, so now I'm going to multiply again. 3 times 1 is 3, and so I put that inside the box, and then I add those together. 0 plus 3 is 3. Multiply again. 3 times 3 is 9. Add those together, I get 5. Then 3 times 5 is 15. Add them together, 23. So your final answer then, if the value of that function when you plug in 3 for x is going to come out to 23. And if you guys look back, so yeah, f of 3 would equal 23. If you look back at your notes from Friday really quickly, you'll see that's the same problem we did by direct substitution on Friday. And so when we did it on Friday, we had to figure out 3 to the fourth was 81, multiply that times 2, and then 3 cubed is 27 times 5, 3 times 4, and the 8. And we had to do whatever it came out to minus, you had to figure it all out, and it took a while, right? This way is way faster and way easier. Okay? So let's take a look at one more example. So this time x is negative 2. Am I missing any terms? I'm missing the x, aren't I? So I've really got plus 0x that I need to remember about. So if I have x to the fourth, what do I assume is in front of that? A 1. So that's my first coefficient. So I've got 1, 2, 3, 0, and negative 7. All right, so now that I set it up for you, and I'll give you the hint, the first thing you do again is drop that first one. Let's see if you guys can figure out what it comes out to. Okay, so as I walked around, it looked like you all came up with f of negative 2 equals to 5. All right, so I'm not going to set this one up for you at all. I'm going to let you do this one totally on your own. Set it up and everything. See if you can figure out this one. Is there anything missing on this one? Nothing's missing. It's 3, 2, 1, 0. So we don't have to plug any zeros in for this one. All right. So we ended up with 57, right? Yeah, everybody had that, I think, when I went around. Okay, so now we're going to talk about graphing polynomial functions. Okay. This is all in your book. You can look at it in section 5.2, so I don't want you guys to freak out. All this information is in there. I want to make sure I have time to show all these problems to you. I think I will, but I just want to make sure I do. So we're going to be talking about the end behavior of the graphs of polynomial functions. So when I'm talking about the end behavior, I'm talking about as x approaches negative infinity and as x approaches positive infinity. Okay, I want to know, what is the graph going to do as x gets smaller and smaller and smaller and x gets larger and larger and larger. So if the degree is odd and I have a positive leading coefficient, my graph is going to, as x is moving towards negative infinity, the y is also going to be negative. So they match each other when I have an odd one. So f of x is going to be approaching negative infinity as x approaches negative infinity. And then on the other side, f of x is going to approach positive infinity as x approaches positive infinity. Which it makes sense. If you've got a positive leading coefficient, is that going to change what the x value is? If x is positive, then it's still going to be positive, right? Because when we raise raise a number to an odd degree, like if I have 3 to the third power, it's always positive, right? If I raise a negative number, so say I have negative 3 to the third power, then it comes out to negative 27, right? So whenever we have odd powers, the negative numbers end up negative, the positive numbers end up positive, right? So that's why the graph goes this direction. On the negative side, everything ends up negative. On the positive side, everything ends up positive. However, if I have a negative leading coefficient, it's just the opposite. That means that f of x is going to go towards positive infinity as x approaches negative infinity, because now my negative is being multiplied by a negative and making it positive. It ends up being the opposite. And f of x will approach negative infinity as x goes towards positive infinity. So this looks complicated, but it really isn't, I promise. Because if you just stop and think about what a graph does, you'll actually probably be able to reason this yourselves. And like I said, this is also in the book, so if you need to refer to it again, you can always look in the book. And I'll be posting a video later. So, all right, so that's for odd ones. Next we'll talk about if we have even degrees. Okay, so we just spent a whole chapter doing parabolas, right? And is the degree even on a parabola? It's x squared, right? Okay, so we knew that if we had a positive coefficient, it was going to go up, right? And if we had a negative coefficient, it was going to go down? Well, it's the same thing for any even degree polynomial. If we have a positive leading coefficient, it's going up. If we have a negative leading coefficient, it's going to go down. So whichever side you're looking at, either way, for the positive one, f of x is approaching positive infinity on both sides of the graph, right? So it doesn't matter if x is approaching positive or negative infinity. It's still going up on both sides. And then just the opposite is true. If we have a negative leading coefficient, it's going down. So that means that f of x is approaching negative infinity as x approaches positive or negative infinity, both directions. All right, so if we look at example 2, it says, what is true about the degree and the leading coefficient of the polynomial whose graph is shown? So basically all they're saying, is it an odd degree or an even degree, and is it positive or negative? So what do you guys think, odd or even? Even, right? Because it's both sides are going down. So this one is even. And positive or negative? Negative, because both sides are going down. Okay? Let's take a look at one more graph. How about this one? What do you think? Odd or even? Everybody says it's odd. You're right. And what about the leading coefficient? How many vote for positive? How many vote for negative? Yes, it's negative. Okay, so because again, over here, our x's are negative and our y's are positive. Those are the opposite of each other. If they're the opposite of each other, it has to be negative. Okay? So it's just as simple as that. It's not anything super complicated. All right, and then the last thing I want to talk about is graphing, because I know you all love graphing. Woohoo! All right. Graphing polynomial functions. Okay, it's actually pretty straightforward. You just plot points. You're not going to have to memorize any shapes or any patterns. You just plug in points and plot them. Okay? So if it's a complicated polynomial, which I think only maybe one of yours is, you can use synthetic substitution to make the table, and it'll go a little faster. All right, so let's take a look at this first one. So first of all, let's think about what the end behavior should be like on this one. I've got an odd degree, right? And the leading coefficient is negative. So I'm going to expect it to start up high and move down low, like that, right? So that's what I would expect to happen. So when I plug in numbers, if my graph isn't doing that, then I need to go back and double check my work, okay? So let me make myself a little table here. I'm going to go sideways because I have more room that way. And I'm going to put in -3, -2, -1, 0, 1, 2, and 3. Okay, so can you get away with plotting 2 points on these? No, you can't. When it's making all kinds of curves, you've got to do at least 5, possibly 7 before you can even see what it's doing. Okay? So this one is somewhat complicated, so I'm going to go ahead and use synthetic substitution to figure out my table values. So if I start with -3, I bring down my -1, I multiply them, and I get +3. Add those, and I get 4. -3 times 4 is -12. 3 minus 12 is -9. And then -3 times -9 is +27. And so I end up with 24. Okay, and then you can go through and you can do that with each of them, or you can do direct substitution, but it'll take you longer, so it's easier. I've already done it ahead of time, so I'm going to go ahead and tell you the rest of the values for the table. What's it going to be when we get 0? No. If I plug in 0 for x, it's going to be -3. Okay, I don't need to use synthetic substitution for that. All right, so the easy ones go, you don't have to use synthetic substitution. If it's going to be 1, it's going to be -1 plus 1 plus 3 minus 3, which is 0. And then we get -1 and -12. So now when I go to graph it, -3, 24, that's way the heck up off my graph, right? So that one's not going to fit. But I can fit most of the rest of them. So -2, +3. But I remember that my other one was way up here somewhere, right? So my graph's from up there. And then -1, -4. So all the way down here, 0, -3, 1, 0, 2, -1, and then 3, -12 is back down here somewhere. So my graph, I just go through the points kind of in the order I did them and draw a curve. Okay, so is the end behavior the way I expected originally? It is, right? I expected it to go that way, and that's how it worked out. So you want to keep that in mind when you're graphing. Think about what the end behavior should be. If when you plug in numbers you're not getting that, then go back and check your math, okay? All right, so yeah, you'll have about 4 graphs tonight. You just need to plot points to graph them, okay? Any questions? No? All right, that's it for today.